In my last video, we looked at examples of how to use the definition of a vector space to prove basic properties about how algebra works with vectors. Now, let's prove some basic properties about the zero vector to see that it really lives up to its name. So far, I've been saying the zero vector as if there's only one vector that functions as the additive identity. But the definition of a vector space only says that an additive identity exists, not how many there are. We could imagine a case where maybe we have x plus o is equal to o plus x, which is equal to x. But we could also maybe have some other special vector that x plus z is equal to z plus x is equal to x. Let's prove that this is impossible. So to prove this, what we're going to do is we're going to assume that there are two additive identities. So assume that O and O prime are additive identities. And part of this assumption is that they're different. If we can derive a contradiction, then we know that there can't be more than one additive identity, which means that the additive identity is unique. And we know that there's one because we're guaranteed that there's at least one additive identity by property 3 of the vector space definitions. So, first, because O is an additive identity, I know that O plus x gives me x. And similarly, I know that O prime plus x is equal to x. So these are both equal to the same thing, and I can set them equal to each other. So I have O plus x equals O prime plus x. Now I know that the additive inverse of x exists, so I will add it to both sides. Now I will use the fact that addition for vectors is associative, so this gives me O plus x plus its additive inverse is equal to O prime plus x plus its additive inverse. Now I use the definition of the additive inverse, so I see that O plus O equals O prime plus O. Now, I know that by the definition of the additive identity, I know that if I have something, being O, plus the additive identity, I just get that something back. So then on the right, if my something is O prime, and I add the additive identity, I get the same thing back. So this is just by the definition of the additive identity. So we see that this contradicts the fact that O was different from O prime. Therefore, there can only be one additive identity. We expect that if we multiply 0 by anything, the result is 0. In our case, if we multiply the scalar 0 by a vector, we do get 0, but it's the 0 vector, since the result has to be a vector. Now, let's prove that if I have a vector and I multiply it by 0, the 0 of the field, then it just gives me the 0 vector. So I know that x is a vector. I'm going to start with 0 times x and work my way until I get to the 0 vector. So let's start with 0 times the vector x. Well, what do I know? I know that this is equal to 0x plus the 0 vector by definition of the 0 vector of the additive identity. Okay, but what do I know about the additive identity? I know that the additive identity is equal to x plus minus x, right? That's by the definition of the additive inverse. So plugging in x plus minus x into here, I have that 0 times x is equal to 0 times x plus x plus minus x. Now I use the fact that addition is associative. So I have 0x plus minus x. Now here's a rule that I haven't used yet. I'm going to use the fact that 1 times x is equal to x. So this is property 5. So I have 0x is equal to 0 times x plus 1 times x plus minus x, and this is by property 5. Now I'm going to factor out the vector x. Right, we're going to use the distributive property, number 8. So this gives me 0x is equal to 0 plus 1 times the vector x plus the additive inverse of x. Now 0 plus 1, that's obviously just 1 plus additive inverse of x. Now I'm going to use property 5 again, the fact that x is equal to 1 times x. So this just gives me x plus the additive inverse of x. And finally, I can use the definition of the additive inverse to have that 0 times x is equal to the 0 vector. And this completes the proof. Just like the previous example, if we multiply anything by 0, we expect to get 0 as the result. In this example, we'll prove that any scalar times the 0 vector is again the 0 vector. So to start, let's start with a times the 0 vector. I know that I'm going to have a times the 0 vector plus the 0 vector, because this doesn't change anything. So this is by the definition of the additive identity. Now I use the fact that I can distribute a scalar over vector addition. So I have a times the 0 vector plus a times the 0 vector. This is by property 7. And this is equal to a times the 0 vector. So now what I'm going to do is I'm going to add the additive inverse of a times the 0 vector. I know it exists, so I'm going to add it to both sides. So I have a times the 0 vector plus the additive inverse of a times the 0 vector. This is equal to a times the 0 vector plus a times the 0 vector plus the additive inverse of a times the 0 vector. Now I use the fact that addition is associative, so I have a times the 0 vector, and I'll just write this as minus a times the 0 vector is equal to a times the 0 vector plus a times the 0 vector minus a times the 0 vector. Now I use the definition of the additive inverse. So if I add a vector with its additive inverse, then I just get the 0 vector. And finally, I know that by the definition of the additive identity, if I have something plus the 0 vector, I get that something back. So this gives me that the 0 vector is equal to a times the 0 vector. And this completes the proof. Thanks for watching. If you like this video, don't forget to hit like and subscribe to see more linear algebra and matrix stuff.